Alright, let's begin this video. I'm gonna do this as a live thing, I don't know what to call it. But let's bring up an idea from the other video. So, if you remember this Cartesian coordinate plane, let's say that we describe a movement from here to here. Say you're going to a friend's house to go, I don't know, play whatever. I don't know what people do. But you forget your wallet because you wanted to order a pizza. And you go back, and your mother just throws your wallet over the fence. Not entirely sure why, so you have to go over the fence. But then you realize there's a dog. So now you have to go even further. And this describes a different direction. Now, I'm not going to go over vectors, but this is basically the idea of a vector. So, could we describe this in an equation? Well, yeah. If you remember from the previous video, we had a slope, and it was defined by m equals delta y over delta x. Now, the way this applies is in this single equation. You'll probably see this quite a bit whenever you're doing like calculus, or actually you'll see a bit of it in linear algebra. I forgot what it was named. So you have this equation. So I don't know why they called it M. I would have just called it S. No, those Italian people or friend. I don't know. It's really all over the place. I think it was some Indian guy that came up with this. Well, anyway, so this is the slope. We don't call this a linear function. It's still going to be a linear equation. Linear functions are related to linear algebra. But x, you just plug in any value, and you end up on this line. And this will be the value of all these. Well, these two. So you multiply it by the slope, and then you add it with the y-intercept. I don't know. Maybe they thought it was going to be called like the bi-intercept or something like that. But how do we solve that? Well, let's say you've got another line. By the way, I'll talk about this in a second, the intersection. But let's say that you have 2 points. You have, 1, 3. By the way, you could come up with any arbitrary value as long as it has a pattern that's linear. So you have 1, 3, and 2, 2. So let's go over the m equals delta y over delta x. So now we have a comparison right here. We have two coordinates that can create a slope that will go infinitely. You have to remember that. It's always infinite if you have an equation. Unless you set some bounds. But, alright. So we have 2 minus 3, negative 1. And then you have 2 minus 1, 1. So now you have a slope of negative 1. Which should be evident because negative slopes will always go in this direction, positive this direction. And if it's only a single value, or if it's a slope of 0, it will always go in this direction. And if it's a slope that's defined in the x direction, then it will go in this direction, that will be an undefined slope, which will look something like this on the Cartesian coordinate plane. So now that we have our, what was it? The slope was negative 1 that we got. Yeah. So let's put that in to our equation. So we have y equals negative x plus b. Now we need to solve for b. It's not complicated because our y-intercept literally just means when it intercepts the y-axis. So you just plug in 0, because when it's 0, then it's always going to be on the y-axis. Because let's say we just keep it constant, then it just is only affected here. We call this, I believe, the codomain, which is the image of an equation. So now this is how you would solve it. So you have 0, comma, b. By the way, I'm just using arbitrary values, and then I'll begin talking about systems. So you have 3 minus b, since we're following this equation still. So 3 minus b over 1 disappears. And right here, you can make a substitution based off what we found for the slope in the first place. So negative 1 equals 3 minus b. And now we have, well, by basic arithmetic, all you have to do is just minus 3, and then it's negative 4, or positive 4, whoopsie. Forgot that this was negative. If there's negative signs on both sides, just assume it's going to be positive. So b equals 4, and you can test this by just plugging in the values, plugging in the x values, and if you get that y value, then it works. Now let's talk about a different idea. Here, let me erase this. Alright. Wow, I need a new eraser. So anyway, let's talk about this idea called a system. A system is just a comparison between two equations. Like, you could do this with multiple equations like this. Like, they had the xy equals 10, not xy equals 10, xy equals 40, x plus y equals 10. That led to complex numbers. I mean, this is some funky stuff. But, let's see, x plus 1, and then y equals 2x plus 1. That's a really simple, whoops, oh no. That's a really simple equation right here, because you could just substitute. This is going to be a method that you can use. I mean, I think I learned this in school. I don't actually remember. Well, so all you have to do is just put this over here or put this over here. It doesn't matter how the substitution works, because if you have a definite y, then you can just put it over here. So let's see, 2x plus 1 equals x plus 1. Subtract x, and then you end up with, let's see, 0, negative x equals 0. So if you plug in the x equals 0s, then you get y equals 1, and then that's our answer. So alright, now let's just backtrack a bit, because let's say that you had 2x plus 2 and then 2x plus 1. Now, here's where the issue comes in, because if you subtract everything here, then you get 0 equals 1. Now, that isn't the best thing that could happen. I mean, unless 0 actually equals 1, but I doubt that it is. Many people have tried. Many people have failed. So if you have an equation where if you can put it into this form, that's great. But what about if you have 3 variables? See, this is where the idea of a matrix comes in, because that actually helps a lot whenever you're solving these. Because then you can just put it into a matrix format, which I will not be showing you guys how to do. Not yet, at least. But we'll just stick to the 2 variable idea. So you can treat this implicitly, where it could be like 2x plus 2y equals 1. And just go off from that if you have another equation, because you're just comparing it, but you can change this up. So 1 minus 2x equals 2y. Divide that. So you have y equals half minus x. Now, it should look something like that. So you have y equals half minus x. Now, let's add another equation. See, I'm not going to do it the implicit way. I'm just going to add it. I'm just going to make it x plus 1. So, plug in our zeros, you get the 1 over here. Positive. You have to remember that. So now, look at the graph. See, right at this intersection, this isn't to scale, or I don't know what term to use, but right here is the intersection, which would be the solution. You could look at it, but what about if you have decimals instead of whole numbers? Then you're going to have to use this elimination method or substitution. I don't know what. I think that's what it's called. But let's talk about a different concept of solutions, because this relates back to the vector idea. Because if you have y equals x plus 1, and then you have 2y equals 2x plus 2. Let's just start plugging in arbitrary values. I'll call this wait, I don't think that works. Oh wait, I just realized my mistake. Wait, no, that wasn't my mistake. Oh wait, my mistake was that I accidentally plugged in 0 over here, even though that there's no possible solution for that. So let's just start plugging in values. So if we have 3 over here, then that's y equals 4. 6 plus 2, 8. So divided by 2, that equals 4. Notice how you can just keep plugging in numbers, and get answers that are equal to each other. This is where the solutions become infinite. And if you don't know what the infinite sign is, it's just that I'm not here to try and make you feel stupid if you don't know notation. I'm gonna cover just everything that comes to my head. But I think that's all I had to talk about. Yeah, I think that's it. So I'll just end it here. If I didn't make any sense, I'll try and go even more in depth if you need help. But otherwise, that's it. God bless you. See you in the next video.